Okay. So, in the last lecture we covered penalty methods, the first family of methods for constraint optimization problem. Now, in this lecture and in the next we will cover primal methods. Okay. So, keep in mind that primal methods work only in the feasible domain, and if some equality constraint is active, then it restricts the step to the tangent plane, so that it does not go out. Even by the tangent plane, it might go out tangentially, because the constraint may be nonlinear, and then it has to bring it back to the constraint surface. And same thing if it is an active inequality constraint, in which the unconstrained optimal point is actually outside. Okay. So, similar situation will come. And then there are quite a few methods in the primal methods, primal set of methods, and we cover some of them. Okay. So, two things you have to keep in mind in the context of primal methods. One is a good news and the other is a bad news. Good news is that in the case of primal methods, since each iterate is at least feasible, so even if your optimization process gets terminated prematurely, the solution that you have in hand as the current iterate is usable. It can be used for the design of the system. Okay. So, that is one good thing, that even an intermediate answer which is suboptimal maybe, that is also useful. The bad news is that you cannot even start the process until you have a feasible solution in hand. There are problems in which to get a feasible solution to begin with itself is a big problem. Okay. So, in that situation primal methods will have a serious disadvantage to begin with, but once you start them, then they will always stay in the feasible region, and that is it. So, if there are n variables in the problem, design space is n dimensional, and if there are m active constraints around the operating point, then the search will be in the tangent space of them, and that means in the subspace of n minus m dimensions. Okay. So, keep that in mind. Now, first thing is variable elimination. Say you are trying to solve a 10 variable optimization problem. There are 3 equality constraints. So, your first wish would be to solve 3 of the variables in terms of the other 7, and then reduce the problem to a 7 variable unconstrained problem. So, that way you will have the advantages of both the sides, number of variables will reduce, that means dimension of the search space will reduce, and there will be no constraints, but that is possible only in rare situations, rare easy situations. So, that method is called variable elimination. However, you will notice that in some of these methods, in the tangent subspace, taking advantage of its linear structure, we will do a local variable elimination. Okay. So, variable elimination on its own is not sufficient as a method as such for general problems, but its seed is used in other methods inside in small steps. Okay. Another method which is actually in some sense that idea that if you cannot eliminate variables, at least eliminate them locally. So, that is used in Frank-Wolf method, which is also called method of successive linearization. What they do here is that at every iteration around the current iterate, around the current point, initially the guess point and next the iterates, they linearize the objective function as well as the constraints, and then get hold of a linear programming problem and then solve that. Okay. So, this is one thing. Now, this is not of great significance, because in really nonlinear problems of proper generality, this does not take you anywhere, because if the domain is concave, then even in the iterations it may go worse. Okay. So, this is a method that way, which I do not give much importance to. Next, we have three methods which are actually good competitors. Okay. One is generalized reduced gradient method, another is gradient projection method, and the third is Zautendijk's method or feasible direction method. Now, these two are in a way similar. Okay. Some key variations are there, but otherwise they are similar. Between the two, I consider gradient projection method as a more mature method. Generalized reduced gradient in comparison is easier. That is why this is what we will cover first. This one is radically different and a valuable method on its own. Okay. Now, what is the spirit of these two methods and what is the spirit of this method? Now, these two methods, generalized reduced gradient and gradient projection methods, their thought process is that the minimum is typically likely to be near the domain boundary. Otherwise, what kind of a constraint optimization problem it is. So, we will operate with the full mindset of operating near the domain boundary and therefore, in the tangent subspace, and at every iteration after our necessary work, we may have the headache of bringing the point back to the feasible domain. Okay. So, this is a typical spirit, typical thought process of generalized reduced gradient and gradient projection methods. So, emphasis is on operations close to domain boundary. Now, both of these methods can be implemented with the slack variable strategy or active set strategy of the inequality constraints. Of course, equality constraints will be always active. Now, what to do with inequality constraints? You have two strategies, slack variable and active set. So, any of the two strategies can be applied to any of these two methods. So, in my illustration, I will show you the first one with slack variable strategy and the second one with active set strategy. But if you want, you can implement the other strategy in respective methods. In stark comparison to these two, this method, feasible direction method, has a clear cut emphasis on the interior of the domain. Its spirit is that, well, it is unlikely, I mean it is not possible that you finally get a point which is infeasible, which is outside the domain as your final optimal solution. That is not going to happen. Finally, you have to get a point inside or on the boundary. Now, even on the boundary is actually extremely close to an inside point, interior point. So, working all the time or most of the time in the interior and going to the boundary only when the optimal point drags you to the boundary is fine. So, this is how the Zautendijk's method or feasible direction method operates. You see, feasible direction, at every iteration you are sitting on a feasible point, that is so for any primal method. Now, in this case even the direction is feasible, that means in that direction whichever way you go, all the while you will have feasible points. So, it will stay always in the interior, it will never, even during an iteration, for a moment also it will not step out of the road into the footpath. Okay. So, that is how it is. And in order to do that, essentially a slack variable strategy will be used. You cannot use an active set. Okay. So, active sets are referred to in this method also, but the actual down to earth nitty gritty arithmetic operations are always done with the slack variable strategy. Okay. So, there is no active set strategy for Zaudendijk method, and this is particularly suitable for inequality constraints. Okay. Only if there are only inequality constraints, then feasible direction method is perfectly all right. So, it avoids the infeasible points even during an iteration, and keep in mind all these three methods that I am going to discuss, as well as these Frank-Wolf method, all of them are essentially first order methods. Okay. So, I mean till now whatever primal methods I have come across, all of them are first order methods only, second order methods are not there, and that is one reason why primal methods are actually a little poorer in efficiency compared to other families of methods that we will discuss later. So, first generalized reduced gradient or GRG method, and I have told you already that we are going to discuss this in this framework with the slack variable strategy. Fine. So, since we are using slack variable strategy, so we have put enough slack variables, and through that we have replaced all the inequality constraints to equality constraints, right, because rather than g x is less than or equal to 0, we are telling plus g x plus a slack variable is equal to 0. Okay. So, that is how you will find that in this description of the problem there is no inequality constraint, because all the inequality constraints have been replaced with equality constraints properly, and the variables are sitting somewhere here. And now, if there were an inequality constraint, correspondingly there was a slack variable, that corresponding slack variable's limit 0 is sitting somewhere. Okay. And now, you will say that why we are talking about lower limit and upper limit for every variable, that may not be part of the problem. Yes, that is not necessarily part of the problem, but still in this framework we include that, because for the operation we need some large number and some small number outside which we will not go. So, think of it this way, that if there is an explicit lower limit or an explicit upper limit for the variable, original variable or slack variable, then that is sitting there in the place of x l and x u. Okay. If it is not there, then you can make a statement of what domain, what region in the design space, search space you are interested in. So, if there is no upper bound for a particular variable, you can always put 5000, right, because your understanding is that the final solution will never go that far. Okay. So, you can put that. So, 5000 or 100 or whatever it is. So, you need a nominal upper bound and a nominal lower bound for some operational purposes, and even without those operational purposes, whenever you really look for an optimal point for a function, even if the original problem is unconstrained, you typically have a sense in your mind that this will be the rectangular space in which I will check, because if any optimal point is going to occur, it is going to occur in this. So, that is typically the region in which the function shows some behavior. After that, outside which it goes on increasing or goes on decreasing, that is the typical way it is. Okay. Because rarely you will find a function which keeps on going up and down in a haphazard manner, unless you have a periodic kind of function, which of course, you will recognize otherwise. Okay. So, we are taking this lower limit and upper limit as mother's milk and continuing, whether they are, no matter whether they are originally in the problem, they have come with the introduction of slack variables, or whether they are a statement of our interest or expectation. If the expectation turns out to be faulty, if you have put 500 and you find that actually at 500 some solution is appearing, then that means that choice of 500 was not a good idea. Next time you will say that no 10,000. Okay. Fine. Now, make note of the dimensions, because this will be referred to all through the slide. N I am taking as the number of variables and L I am taking as the constraints here. Okay. Fine. So, now you start with a feasible point x 0 satisfying all these constraints and all these bound constraints also, fine, and set the iteration number 0. And now, the loop which starts here and ends all the way here. Okay. And there is a lot of work, lot of little things to be done. First of all, you partition this design space into two parts, y and z. Y is of L dimension, that means as many constraints are there, as many equality constraints are there here. Okay. So, that many y's and the rest of them are z. Now, suppose you are solving a 10 variable problem in which there are 3 equality constraints like this. So, you will say that I will split the 10 variables into segments of 3 and 7. Okay. Now, it is not necessary that you take x 1, x 2, x 3 here, you can take any 3, and which 3 to take, that you will do a little judiciously. One thing that is necessary is that the gradient of this h with respect to the y variables should be a non-singular matrix. That is actually a key matrix. That is why this is L dimensional. Say h is L dimensional, y is also L dimensional. The idea is that among 10 variables you have 3 constraints. So, locally up to a linear approximation you would try to use these 3 equations to solve 3 of the variables in terms of the other 7. And in the process of solving that, there will be a 3 by 3 matrix which you will need to invert. That matrix is basically the matrix of the first order derivatives del h I by del y j, and that matrix should be that 3 by 3 square matrix, little square matrix should be non-singular. That is one overriding necessity. Now, there may be many such choices. It could be 1 2 3, it could be 1 2 5, it could be 1 5 7, it could be 1 9 10. There could be many choices which would satisfy this requirement. Okay. And this is a little cumbersome. Okay. So, if there are many such choices which satisfy this essential basic requirement of the invertibility of the gradient of h with respect to y, okay, not the z. Okay, that is not of great use in this context for non-singularity, and that question of non-singularity will not arise, because that will be not 3 by 3, but 7 by 3. Okay. So, this one should be non-singular. If there are many such choices which satisfy this requirement, then you choose a set of 3 as y, such that the other 7 which remain in z, they have good margins from their lower bound or upper bound, lower bound as well as upper bound, that is they are well in the interior. Why so? Because if you are going to solve the y variables in terms of the z variables by the use of this, then where will you conduct your search? Where will you conduct your iterations? You will conduct your iterations among the remaining 7 variables z. So, it is the z variables in which you will really conduct the search, in which you would like to move around, and therefore, it will be a better thing to have more freedom in the z variables. So, that is why you should prefer y such that this is invertible, and you should prefer z such that z k's are away from the bounds as much as possible. Okay. So, by this you can make a good choice, and it is not necessary that you make the best choice here, any good choice will do, fine. Now, that you have partitioned the variables, you partitioned the grad h also like this, and we use a little figure to have a sort of understanding of what is happening here. You see, all the y variables that we will call as locally dependent variables, which we will be solving in terms of z. So, all the y variables I am going to show here, and all the z variables I am going to show here. Okay. Now, h is actually a function of x, that is h of y z, h of x. So, you can now say h of y z. So, this third direction can be taken as all the h's like this. Okay. F also we can see in that direction only. Now, h as a function of y and z will be a surface in this. Okay. So, like this, and now that surface, the entire surface will not be feasible, because that surface, the part of the surface where h is equal to 0, all the h's, all the 3 h's 0, that is the surface really. Okay. So, now h 1 as a function of y z, if you plot, cut 0, h 2 as a function of y and z, cut that at 0, and so on. So, what points you get there, these together form the surface for you. And when you say that I am cutting like that, then basically in that surface you will get y as a surface of z, that is y as a function of z. Okay. And we will be talking about the tangent of that, okay, tangent of that surface. So, now you partition this also, that is grad h is typically 10 row long thing. Okay. So, now its transpose has been taken. So, if there are say 3 constraints among 10 variables, then grad h will be 10 by 3 tall matrix, its transpose will be 3 by 10 short fat matrix, and in that the first 3 columns, of course, you have to organize that first and later according to this partitioning. Okay. Now, the 3 columns corresponding to y variables in the derivatives, they will give you gradient of h with respect to y. These are the 3 by 3 block, okay, and these are the 3 by 7 block with respect to the z variables. See, all through transposes are there. Okay. So, call this 3 by 3 square block as B and this 3 by 7 rectangular block as C. Okay. And now, because of the definition like this, you can say that a little movement in x is composed of little movement in x in the tangent plane will consist of this matrix into delta y plus this matrix into delta z. Okay. So, that is here this matrix into dy plus this matrix into dz. Okay. So, a movement like this, this distribution of dy and dz will mean a movement in the tangent space, okay, in the appropriate ratio. So, this is the tangent plane. Now, you say that I am going to take a move in the tangent plane, okay. So, which will satisfy this, that is some dz movement we will choose, corresponding to which the dy movement we will find from here, and that is where you will need the inverse of B. Okay. So, first what we will do? We will say that if we are going to move in this tangent plane, then in which direction to move in the tangent plane? The tangent plane also has thousands of directions. So, you will say that I will consider the gradient of the objective function with respect to z, total gradient. What is the idea of total gradient? Total gradient is that f is dependent on x, that means y and z, but in order to keep it in the tangent space, y itself is dependent on z, that is this. Okay. So, f of x is essentially f of y of z and z, and we want ultimately the derivative with respect to z. Okay. So, as we change z, then how is f going to change? One is because of this direct contribution, that is this, okay, gradient of f with respect to the z variables, 7 z variables, plus gradient of f with respect to the y variables multiplied with the rate of change of y with respect to z, that is this. Okay. So, this will give you the total variable, total derivative, fine, and this is called reduced gradient, because this is not grad f x, but it is reduced in the reduced set of variables z only, okay, considering y's as dependent on z. So, that is why it is the reduced gradient. Now, we have got this reduced gradient, fine, and now we say that in this reduced gradient we would like to move, okay, and this del y by del z is from here, you see this dy by dz, that will be minus B inverse C, minus B inverse C transpose, this transpose is here. Okay. So, del y by del z is minus B inverse C, then its transpose, and then this ordinary gradient. So, this is where you will need B inverse. Okay. In another place you will need B inverse. So, now this is the derivative of objective function f with respect to the really independent variables. Okay. So, we will go in the negative gradient direction, that is direction negative to this minus r, but then you cannot take minus r on your own if that takes you away from the domain, outside the domain. So, if some of the z variables are right now at the lower limit or right now at the upper limit, then beyond that limit you cannot go. So, by default we would take the dz, that direction in the z subspace, as minus r, but subjected to this joint limit, I mean not joint limit, the variable limit. Okay. So, by default we will take each component of the vector r and put it here with negative sign, except if the particular z component is sitting at the lower limit and r I is positive, that means minus r I would be negative, which is not allowed. In that case, keep it 0, that is it is at the lower limit and still lower we would love to go, but we cannot, higher we would not like to go. Okay. So, keep it at 0. On the other hand, that is the direction, the step to be 0. Okay. Similarly, if it is already at the upper limit, then the change is kept 0, already at the upper limit, and minus r I would take it further up, okay, in this case. So, then also you do not make any change. So, that is how you decide the direction in z. Okay. So, you have decided the direction in z. Now, a unit step in this z direction if you go, the corresponding y movement you calculate from here, that is minus B inverse C into whatever dz you have chosen. Okay. So, this gives you the corresponding movement in y. So, you have got a movement in z, you have got a movement in y. Now, compose both of them and you get the full movement in the x space, okay, in the appropriate order, right. And now, this is direction. After all these things, you have got the direction along which you are going now in this iteration. So, along that direction you conduct a line search. Okay. That means, you define a single variable problem like this, alpha f of x k plus alpha d k, and conduct a line search. This bit is nonlinear. Okay. Till now everything else we have done linear, derivatives and linear. Now, this is single variable nonlinear optimization. Okay. So, this is line search, ordinary line search. You can do it by golden section method or whatever it is. And for that you choose an upper bound, and the upper bound should respect all the variable limits. Okay. So, with all the variable limits in hand, you choose the upper bound of this line search and conduct, and lower bound is of course 0. So, and then you use your favorite golden section or whatever and get hold of alpha k. After you have got alpha k, you will say that now the candidate for the next iteration is x k plus alpha k d k. Fine. However, you will check that it is feasible or not. It may be infeasible. I will show you how it can be infeasible. Say currently this is your constraint surface, this is the boundary along which you are operating. Now, this is your x k. You have taken the tangent space, in that you have evaluated the reduced gradient and whatever, fine. And then in that you have conducted line search and you are supposed to come here. Okay. Now, this is the candidate x k plus 1 candidate. This is certainly outside the domain, okay, because it is not on the surface. In two cases it can be outside the domain. One, this is an equality constraint, in that case it is certainly not in the domain. Two, it is an inequality constraint and this side is infeasible, this side is feasible. So, in that case also it is out of the domain. So, now from here you will need a nearby point which is in the domain or on the boundary of the domain. Okay. So, that is the next exercise that you have to do. What you need to do? You need to get a solution of h of y z equal to 0. Okay. This is what you need to do. So, z k you already have as a starting point, y anyway will be dependent on z, okay. Or rather z you have found, you have to find the corresponding y. Okay. So, y is say in our example 3 dimensional, h is also 3 dimensional. So, with if you keep the z fixed and change y, now you will basically leave the tangent space. That is why the ratio of z and y you are not going to maintain anymore. Okay. So, now it is a tangent subspace which is the problem. You have to leave the tangent subspace to come somewhere here for the x k plus 1. Okay. So, you have to leave the tangent subspace, though, so you do not respect the ratio of dz and dy anymore, and say close by give me a point which is fine. Z I am keeping as it is, the 3 variables y we will solve by these 3 equations. That is standard Newton-Raphson solution. Okay. So, conduct this Newton-Raphson solution to get y k plus 1. Okay. Now, if it converges somewhere, the Newton-Raphson iteration somewhere here, if it converges, whichever point it converges, as long as h of y and z is 0, you accept it, fine. Why did I say if it converges? Because it need not converge. I will show you another situation of this constraint surface. Okay. So, this was the constraint surface. You were at this point x k, conducted the line search etcetera, got here, and from here you tried to use a Newton-Raphson iteration to get down here, iteration, 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 no, it is diverging. Okay. So, it is possible that it does not converge. If it does not converge, then what to do? Then you say, oh, no, if we take such a big step, then it may not converge. Take a half step and then from there try. Half is just a convenient factor, you take your favorite factor. Okay. So, take a half step from here and then try again. So, in place of alpha k, use alpha k by 2, put it here back as the candidate, that is like taking this half and then from here trying the Newton-Raphson iteration, okay, and that is it. So, you go on doing this and that is it. Okay. So, this is now after doing this, the result that you get in hand, the composition of this new iterated y k plus 1 through Newton-Raphson method and the z k plus 1, which we got from here and kept in hand. The composition of these two together give you x k plus 1 and then you come all the way here and start the loop all over again. That means, partition also may be fresh. Okay. So, this whole thing you have to do in every iteration. So, this is generalized reduced gradient method or GRG method. Okay. So, we leave this here and in the next lecture we will cover the other method, gradient projection method. Okay.